Okay, let's start. Hello everyone again. A lot of you are early birds, as I see. Please, before I start this presentation, please raise your hands, those of you who are using classic or super classic in production. Great. This session is dedicated to your attention. Is there anybody here using super server for production? You may keep sleeping or drinking beers. Okay. This presentation will consist of two parts. In the beginning, I will explain how the log manager works in Firebird, what goals does it serve, and what are its key pieces. All this information is required to better understand the second part of this session, where I will be presenting some small practical part on how to use a log print utility and how to analyze its output and how to use it to diagnose any problems or improve the performance of your Firebird Classic or Super Classic installation. Yesterday, in my first presentation, I paid some minutes of attention to the synchronization, mostly shared cache synchronization. But actually, Firebird has a lot of shared resources that different connections or different threads must be accessed into simultaneously. So, of course, as every piece of software, Firebird has quite complex synchronization mechanisms. They can be divided into two parts. The first part is synchronization primitives used inside a single process, inside a single address space. You know them well: mutexes, spin locks, read-write locks, and the latches. I was speaking about that yesterday. Of course, different events and so on. But Firebird also offers a classic mode, which means that different processes accessing the database, and surely that means that these processes must synchronize their concurrent access to different resources. Mostly it's about database pages, but not only that. So the external synchronization is performed by the log manager. Actually, the Super Classic also uses the log manager, but it just avoids any inter-process communication because everything resides inside a single address space. But the log manager is still used because, as you know, Super Classic has separate page caches. Why we use the log manager, and in what kind it's unique to the different locking primitives? First of all, unlike mutexes or unlike read-write locks, the log manager supports multiple states, multiple kind of locking, shared and protected read mode, shared and protected write mode, and the exclusive mode. Of course, some of them are compatible with each other and some of them are not. The most commonly used lock types and lock states are shared read, protected read, and exclusive locks. And the log manager supports all these kinds of locks and allows to detect whether the current lock request is compatible with the current lock, and if not, what actions should be performed in this case. The log manager supports so-called blocking notifications. It means that if one process, if one connection holds some kind of lock, and another connection also needs this resource, to access this resource and trying to acquire the same lock, but of the different level. For example, the first process has a shared lock, but the second process acquires an exclusive lock. It means that the first process should somehow allow the second process to have the log granted. How it is performed? It's done via the blocking notifications. If the second process request a log that is not compatible with the current log state that's held by the first process, then there is a notification sent from the second process to the first one. Actually, there is a flag in the log table to indicate that the first process is blocking us, and there is some kind of event sent or maybe semaphore flagged to guarantee the IPC communication, that the second process can really deliver some signal to the first one. And after that, the first one just scans the log table, sees that some flag is set, so somebody is requesting the incompatible access type, and the first process is required to immediately or a bit later downgrade its log. Downgrade can be either release or downgrade from exclusive to the shared access. For example, if the first process held exclusive log, the second one requires a shared log, the first process does not need to release its log at all. It just needs to downgrade it to the shared log because they are compatible and both will be holding the same log type. It's okay. But, of course, in some conditions, the process cannot release or downgrade its log immediately. For example, it's a page log and the process is now working with the page, modifying the page. In this case, the receiver of the blocking notification, it's so-called AST, asynchronous system chat. It's a kind of callback or signal handler that asynchronously calls the engine to deliver the signal, the blocking notification. In this case, if the log cannot be downgraded or released immediately, the resource behind this log is flagged for delayed release. So as soon as the process no longer needs this log anymore, it will be released. Usually, this time frame between a request and the time the log will be released is very small. Not immediate, but quite small. So in practice, it doesn't cause any performance problems, but it's actually the only way to guarantee that the log manager can work across the processes. Another feature of the log manager is deadlock detection. By default, it's done every 10 seconds, but only in the case if somebody is blocking us for a very long time. So if we are requesting some kind of log, the log cannot be granted immediately. We send the blocking notification. The AST routine has flagged the resource, and we are waiting until it will be released or downgraded. But if we wait more than 10 seconds, the log manager decides that there's something suspicious and perhaps the process died, perhaps, or perhaps it's still alive, but some kind of deadlock happened, and the log manager forces a deadlock scan in this case. So actually, deadlock scans are not happen just regularly by the timer, no. Only if some request is not be granted after 10 seconds. It's a very unusual situation, and so actually these deadlock scans are not run often, and they do not affect any performance in any kind, but they allow to detect the processes and detect real deadlocks. They're very rare, but they still could be possible. And of course, if some process is known to cause any deadlock, is indicated, the log manager indicates that this some of these processes can be just rejected. The request can be rejected, so the others could report an error to the upper levels, and so on. So not only detecting deadlocks, but also rejecting the request causing the deadlock after this interval, by default is 10 seconds. And there is an ability to monitor the log table. It's done with a FB log print utility, and I will be talking about that later. What kind of logs Firebird use? Actually, there are many of them, maybe 30 or like. Almost any shared resource must be protected with the logs. So different goals. For example, we have so-called existing logs. It means that every table or procedure, for example, index or collation, whatever, your statement is accessing, as soon as your statement is passed and compiled into the executable form, your request acquires the shared logs on all resources utilized by this request. So if your statement uses some table, you will have a shared log on that table. It guarantees that a concurrent drop statement will not drop your table while it's in use. This is actually the reason why some concurrent drop or alter statement may be reporting object in use. This is guaranteed by existing logs. As soon as your statement is completed and you have closed its handle and your transaction is committed, this log is released, thus allowing any metadata modifications. There are also table access logs. It allows to synchronize incompatible operations on the tables. For example, when you create an index, if concurrent inserts or deletes will be allowed, your index will become broken. But at the same time, nothing should prevent you from selecting from these tables. And this is exactly how table access logs work and what do they provide. They synchronize that if some operation like index creation requires some kind of log that should be more or less restrictive, it's done this way. Also, if you use table reservation options in the transaction parameter block, it's also provided. It's also done via the table access logs. Transaction logs, of course, every transaction holds its own logs, and they are used to analyze whether the transaction is still alive, for example, and it's active and running, and a lot of other objects actually, mostly related to the metadata, and some other things like shadows, sweeping, and so on. But the most important part, the most important log type is a page log. Every database page has corresponding log in the log table, which allows different classic processes to share the database file. So there is low-level synchronization only at the page level, but of course, multiple processes can actually try to modify the same set of pages, because some pages are quite hot in the database for the concurrent access. So page logs are very important. And actually, it's the page logs that are causing any performance problems in Classic. This is just an example of the log times. As I said, there are a lot of them. This is just the first few. Just in my next part of the presentation, I will be talking about page logs is LCK BDB number 3. Please remember this number. I will be referring to it later. Just a few words about the super server. It has a single process, the single address space, and it has a shared page cache. So it doesn't need any page logs through the log manager. It still uses the log manager for some other operations, for metadata, existing logs, transaction logs, and so on. But page logs are not used in super server. They're just redundant, so it's just an optimization. Also, even those kind of locks that are used by the super server. As everything resides in the single address space, the blocking notifications are dirty cheap because it's just direct call of the appropriate procedure. No IPC is involved. With classic or super classic, page locks are used. They are widely used. Actually, the more connections you have, and the bigger is your page cache in classic or super classic, the more page locks exist in the log table, and the more they affect the overall performance. So from one side, you may notice that increasing the page cache could allow your queries to run faster because of the less disk reads, for example. But from another side, the concurrency inside the log manager is if your application, if your database is highly loaded, actually this concurrency will be much noticeable, and the log table could become a kind of a bottleneck. I will be talking about that a bit later. And if we speak about classic multi-process architecture, then in order to deliver blocking notifications, IPC must be involved, and costs quite a lot. And this is why one of the reasons why Super Classic has been implemented in Firebird 2.5, because in the single address space, notifications are cheap and they are much more efficient. And of course, as we have a lot of page log, the log table grows, and you should pay attention to tuning it properly for your load and your database size. This is just a picture of the common architecture, basic architecture, between two classic processes. Actually, the entire log table is located in the shared memory. It's accessible by both processes, actually, but by all processes. This shared memory can be read or written. It's protected by a mutex, that is cross-process mutex. Blocking notifications and the IPC communication can be done directly between the processes, and it could be done through the process FB log manager. There is some confusion in this regard. Actually, this process in Linux and the other Unix systems, it's not a log manager. A log manager resides in every classic process. The only need for this FB log manager process is to guarantee that signals can be delivered between different users, between different security patterns, different security tokens. For example, you have a Firebird server started by the X inetd daemon, TCP daemon, and by default it's running under the Firebird user account. Everything is good. Everything works with the Firebird credentials. Now you log into the console with the root access and start a GBAC to back up your database. In Classic, in Linux, GBAC will load the embedded engine of the server and will be accessing the database directly through this embedded engine. It will not work through the TCP. As a result, you will have another copy of the Firebird Classic process hosted not by FB in a server, but GBAC, but which is running with root privileges. And if in the same time the worker processes, your user connections, will have to deliver some signal, some blocking notification to GBAC to release some page that is reading at the moment, signals in Linux cannot be delivered from regular users to super user. It's a security problem and an error will be thrown. In order to avoid this situation, FB log MGR process always should be run with the root credentials, and the Firebird setup utility installs it this way, setups it this way. And in this case, Firebird delivers signals through this privileged process. It's just a bridge It doesn't handle logs. It just reads the logs table and delivers signal to anyone because it has the higher possible permissions. It's a root process. So just be aware about that. Actually, if you for some reason shut down the Firebird installation and killing all the working processes, you shouldn't be afraid of killing the log manager. It doesn't actually modify anything in the log table. It just delivers the signals. So also it can never become a bottleneck in your problem. So you shouldn't pay much attention to this process. It's a kind of utility. It's not a core part of the log manager. Just some kind of agent that coordinating access to different security credentials. Okay, we have a log table. There is a region of the shared memory protected by global shared mutex. What can be seen inside the log table? What kind of objects can you see there? Of course, the structure, the physical structure of the log table is quite complicated and it changes from version to version, so you don't actually have to learn the Firebird source code in order to understand how to analyze the log table, how to read it. You just need a few basic information about that and how to analyze the output of the log print utility. It does everything for you. What kind of objects you can find in the log table? There is a header section in the beginning of the log table that contains some core information about the log table. It enlists the major objects that are located there. It defines what is the current size of the log table in memory. It defines how many bytes are actually used at the moment of that shared memory, and so on. Besides the header section, there are three kinds of objects in the log table: owners objects, log objects, and requests. Log objects, also known as log resources. What is owner? In the log table, owner is a connection. So if you see, for example, that the log table lists you 10 owner blocks, it means that 10 user connections are actually accessing that database at the moment. So, for example, if you use some older Firebird versions prior to Firebird 2.1, where there are no monitoring tables, you can easily detect how many users are connected from the log table. A simple call by the FB log print utility without any parameters will report to you the header block and will show you how many owners actually inside the log table. Log resources, it's actually what kind of object and what particular object requires synchronization and the processes can access. For page logs, for example, a log resource is a page. It could be, for other log types, it could be relation, table, transaction, and so on. Requests, log requests, are user attempts, actually not user, but Firebird process attempts by caused by some user statements or transactions. Requests are attempts to grant the log to some process. Actually, for example, we have a header page in the database, its number is 0, and you have 10 processes constantly reading or writing the header page. So in the log table, there will be one log resource dedicated to page number 0, and there will be 10 log requests by the 10 different owners to access this log. So requests are just attempts to have this log granted or perhaps rejected in the worst case. Another thing that you should be aware about, the log table originally, initially, when it was created by the first connection, it has a fixed size and it can grow by demand in the future when your load grows and you have more connections and more page logs, for example, and they don't fit the lock table at the moment, it's extended. It's extended in the pieces of the fixed size. But the operation to extend the lock table is quite expensive. It requires to synchronize all the processes trying to access the lock table at the moment. It tries to synchronize all the threads inside a single process that can be accessed in the lock table. And for example, if some process is waiting for its request to be granted, the lock table cannot be remapped immediately. Those extensions are called remappings because actually the lock table is still the same, still allocated as a whole in one piece. If it was, if we had a small lock table at one time, it just gets remapped in another address space with another size. So it gets bigger, but it's still the same block. It's still a sequential block of bytes. It's not splitted in parts. Why? Because all the objects inside the lock table are referred by offsets. There is a base address of the beginning of the lock table, and every object in the lock table is addressed by its offset. So the lock table is always contiguous in memory, and it's not split into parts. And lock resources, we have a lot of lock resources inside the lock table. In order to locate them faster, there is a hash table. So every lock resource has its associated lock key. For example, for the page locks, it's page space and page number, 2 values. The lock manager creates a hash key from these numbers and the lock type, and it maintains the hash table of all the lock resources stored inside for any for faster access. Just an example for the page locks, we have a lock resource object inside the lock table. Series is the lock type. It's known to be a page lock. It's number 3. The lock key is a page space 1 at page number 75, and it's currently locked with the protected read mode. A few lock requests are linked to this lock resource, to this page. 2 of them are already granted. You can see that the lock is acquired in the protected read mode, and 2 lock requests are granted in this mode. They're compatible requests, so we have both of them granted. So we know that 2 owners, process number this and this, now read this page. They both are allowed to read it. At the same time, other processes, 2 other processes, try to lock this page in the exclusive mode. They require a write access. They need to modify this page. The exclusive mode is not compatible with the protected read mode. So they are actually in the pending state. They're just waiting for the lock to be granted to them. In order to do that, these 2 locks must be released with the blocking notification. A few words about the state of different objects. I will talk about that later. This is just for your information. The states are actually not really states. It's some bits in the flag for these objects. The owner is known to be waiting when it requests some locks that cannot be granted immediately. So it delivers the blocking notification and starts to wait for its lock to be granted. So we have in the flag field, the waiting mode is the value of 4. And now just a few examples. In my opinion, they are the most important for you to remember and to understand, because I will be referring to them a bit later. The owner is known to be signaled if we have decided that he is blocking us and we have sent him them a blocking notification. this is reported in the log table as the log owner has been signaled. So when it gets signaled, it calls the blocking notification locally in order to release or downgrade the appropriate log. Log requests could be either pending, it corresponds to the owner is a waiting state, so we trying to grant access to some log, but somebody is locking it in the incompatible way at the moment, so we have to wait. So our request gets the pending state. The request, in this case, who is blocking us, it's marked with a blocking flag, and as soon as the blocking notification has been delivered to the blocking owner and the appropriate routing has been called, the blocking flag gets cleared and the blocking scene flag gets set. In this case, we know that not only the signal has been delivered, but actually the asynchronous procedure, the AST, has been called and it tried to downgrade or release the log. So if the log still not granted to us, it means that it couldn't be released immediately and we are still waiting that the process will react with a delayed log release. In this case, we are still waiting, but we know we already know that everybody blocking us has been notified and reacted appropriately. So everything went well. We just need to wait. A few words about the possible options to tune the log manager for performance. As I said, one of the important settings is the log table size. Initially, in all recent Firebird versions, it's 1 megabyte. In older Firebird version, it was 32 kilobytes, if I'm not mistaken. In order to avoid often remaps of the log table, it would be better to set the appropriate log table size in advance. Some of our users have reported that actually tuning the log memory size in advance to the big enough value to avoid remapping at all has noticeably increased their performance in Quiz Classic. The formula commonly used in this case, you should check what is your page cache size in pages, multiply to the maximum number of connections that can be accessed in the database, and multiply it to 100. Actually, for 64-bit systems, I would rather multiply it, for example, for 150 or something like that. If you have enough memory, free memory on your server, it wouldn't hurt to increase the log table even more. For example, you get some number by this calculation, it says you that you need 500 megabytes for the log table for the highly load system, and you have a lot of RAM in your server. Don't be afraid to set up the log table to use a 1 gigabyte of memory. It will only be good. Later, you could analyze with the log print utility how many memory is actually used and decrease it if required. But from the beginning, it might be better to have this value set up initially to be big enough. If you are running all the Firebird versions prior to Firebird 2.5, you will also need to increase the number of semaphores that the log manager can use. By default, it's 32 semaphores. But if you have any problems that are usually reported in the Firebird log file that the system is out of semaphores, then you should increase this number. At the same time, you should check how many semaphores are currently enabled for your Linux or your other operating systems. I don't remember, by default, in the old times there were 64 semaphores. Maybe it could be different in different operating systems. So in this case, you could either change these parameters and recompile the kernel, but it was quite old enough. Some recent Linux distributions don't require any kernel recompilation for these settings, as far as I know. In Firebird 2.5, you don't have this setting in firebird.conf file anymore at all. You shouldn't care about handling semaphores at all. And if you have a lot of logs in your log table, it mostly means that you have big page cache and or big number of connections. Please pay attention to increasing the log hash slots value. It's the size of the hash array, hash table. In older Firebird versions 1.5 and 2.0, the upper limit of this setting was about 2000, as far as I remember. In recent versions, Firebird 2.1 and 2.5, the upper limit is much higher, so you are unlikely to hit the upper limit. So set up it to whatever prime value you need by the length of the hash collisions chain. I will be showing it in the next slide. And one more thing. There is an environmental variable Firebird log which defines where the log table is located. By default, in Firebird versions prior to Firebird 2.5, it was located in the root directory of the Firebird installation. It gets created with the first connection and gets cleared, but usually not deleted after the last connection. In Firebird versions prior to Firebird 2.5, the log table was single for all the databases on this server instance. In Firebird 2.5, every database has a separate dedicated log table. So access to different databases do not concur for single shared resource, the shared log table and the shared mutex. But this environment variable allows you to override the default and relocate your log table if required. Actually, this is quite dangerous option because the environment variables can be set different to different values to different users, or maybe even to different processes. And if you two classic processes will be using different log tables to access to the same database, you will get a corrupted database in a few minutes. So don't try this option unless you are really sure what you are doing, and unless you can guarantee that every process of the Firebird server of any utilities like GBAC and so on, any embedded user connections, see the same value of this variable. This is absolutely important. Why you might want to change this variable? There was a report by one of our customers that relocating the log table to the RAM disk allowed them to increase the performance about 50%. They had a very high load, many connections. All the tuning I was talking about has been done, but the mutex weight ratio inside the log table was still high. So the contention was still noticeable. The log table was actually more than 2 gigabytes in size. But anyway, they have allocated 4 gigabytes for the RAM disk and reallocated the log table there with the Firebird log environment variable and got a noticeable boost in performance. The mutex weight ratio was lower. So I wouldn't recommend you to play with this option unless you're really sure that the log manager is a bottleneck for you. And all other options are tried, but they didn't help. But you should remember about this ability. A few words about the logprint utility. Its only goal is to read the log table and report it in the human readable form. It doesn't modify the log table, so it's safe to run it whatever time you need. It can report different things, different objects of the log table. By default, it prints only the header block and enlists all the owner blocks. But there are many options if you want to print only owners, only lock requests, only lock resources, if you need to print everything with the A switch, if you want to get only the waiting lists and possible deadlocks detecting is done with the W switch, and so on. This slide is mostly informative for you. Just do not forget about these abilities, because the log print utility prints it in the output or in the command line. But as you know, there is no good documentation for the log print utility at all. So this information could be useful for you later. Just download this presentation after this conference. A few other options for the log print utility. It can be working in the interactive mode with the I switch. It just not exits immediately after printing the required information. It starts to read the log table with a defined interval and prints the output in these points of time. Other options. First of all, what log table do you need to read? It is a D switch. After that, you must specify the database name on the server, full connection string without the host name. It's true for Firebird 2.5. Another option is to specify the log file. If the log table has been dumped to disk, for example, after a server crash, you could read it. You just copy the file, the log table file, and you can attach to it with the log print utility by specifying the F switch. It's also about Firebird 2.5. In previous Firebird versions, as I said, the log table is all for all databases, for all the databases. It's located in the Firebird installation root. So the log print utility knows where the log table is. It doesn't ask you for any options. It just reads the log table without any switches. There is also a C switch, stands for consistency. The only change this switch allows you is that it locks the shared table, the log table mutex before reading the log table. Without that switch, the utility works in the dirty read mode. With this switch, it gets a consistent result. What are the possible problems with or without this switch? Of course, if we speak about dirty read mode, the results sometimes could be quite funny. Hard to understand, hard to explain. Actually, I know cases when the output just enters into some infinite loop and the output never ends, and so on. So usually it's better to use the C switch, but the mutex of the log table will stay locked until the whole log table will be read and analyzed. In the highly loaded systems, it would mean that all the user processes will be blocked until the log print utility will end. So pay attention to that. If you will be just playing with this utility in order to understand how it works on the production database with the C switch, users are going to kill you. And one more switch, M switch. It's actually a display trigger. It allows to generate the output in some kind of semi-HTML mode. I will show it later. Just offsets of objects are represented with hyperlinks for easier navigation. It doesn't make any sense in the console mode, but if you redirect the output to the file, it allows you to better navigate through the log table, just allow some level of convenience. Okay, now let's see a bit of practice. The first example, we just start the concurrency test with 10 connections. Okay, well, it's working. Now, I'm showing this example with Firebird 2.5. So in order to access the logs table, I have to specify the database name. Here is a call for this utility. No other options are provided, only the database name. So the log table header will be reported and all the owners will be listed. What can we see here? Here we have a log header block. The length field, how many bytes are actually allocated into shared memory. As I said, by default it's 1 megabyte. So it currently has the size of 1 megabyte. It's how much memory is actually allocated from the operating system. Right now, the log table is using only 200 of thousands bytes, a little bit more. So a quarter of the whole allocated amount. So there are unlikely to be any remappings in the short term. But if you run this utility in your production database and you see that the log table size is much bigger, for example, 10 megabytes or maybe 200 megabytes, depending on the load and the cache size, you now understand that if you left the default settings, then tens or hundreds remapping already happened, and they may happen again. So it's really time to go to the firebird.conf file, increase the log mem size parameter to the level bigger than the maximum value you have ever seen in this field for your database. Of course, you could send it to some lower level and then analyze how often it goes beyond this value, but I would really recommend setting it always higher than the one used here. If you have set it too much higher and you notice that it's never changed, so there are no remappings, and the maximum value of the used length is always much lower, then you could decrease that value. If you need some memory used for the page cache, for example, or lock intake or sorting model and so on. So if it's tuning, how it should be done for tuning the log table size. Here in the middle, we have how many hash slots are allocated. By default, it's 1009. When deciding whether you should to increase this value or not, you should pay attention to these three values. The length of the collision chains, the minimum known, the average, and the maximum. Currently we see that the collision chains are extremely short, so almost every log can be located through the hash table directly without scanning the collisions. This is good, and you should not change the hash table size. If you see tens or maybe even hundreds here, especially in the average and maximum length, then you should be changing the number of hash slots, increasing. It could be questionable for tens. For example, if you have 11 or maybe 20 collisions in the chain, it could be performance problems, but it could be not. So it's actually some boundary value that's still not big enough to worry about. But at the same time, it doesn't hurt to increase the value. But if you see hundreds here, then obviously you must increase the hash table immediately. It will increase your performance at the moment. I just remind you to use the prime numbers as bigger as you can, provided that the values are kept quite low. They do not get bigger than 50, for example, or 100. Another counter, not really counter, the mutex weight ratio, here also in the middle of the header section, shows you the concurrency problems with the log table. Currently, we see that there is almost no contention for the mutex protecting the log table. It would be interesting to see whether it changed after the test started. No, nothing really changed. Okay, but if you have, for example, 5%, 2%, that's good enough. If you have 12%, then you should be started to what can be tuned. You should be analyzing the hash length, whether you need to increase the hash slot value. If your mutex weight ratio is more than 20 or 30, it really means that you have problems with the log manager. It becomes the bottleneck for your classic processes. And if everything has been already tuned, you have increased the log table size, you have increased the hash slot value, so you have very short collision chains here, but the mutex weight ratio is still high, then perhaps you need to analyze your log table further, or perhaps you would need to move it to the run list, for example. What else can be seen in the log table header? Number of owners means that there are 11 connections currently accessing the database. Deadlock scans 0, deadlocks 0, scanning 0, default 10 seconds. It means that no log request has been waiting for its log to be granted for more than 10 seconds. There are no deadlock scans. If there will be deadlock scans, but the deadlock count is still 0, it means that some logs were waiting for a long time, and a deadlock scan happened. But if no deadlocks were reported, perhaps it could mean that either some process has problems with releasing its log in time, it's overloaded maybe, it's maybe stalled, frozen for whatever reason, and so on. Or it could mean that some process has died and 10 seconds must have been passed before we could try to detect the dead processes. After that, the log table will be correct that all the resources occupied by the died process will be released and cleaned up from the log table, and all the logs will be granted to the waiting processes, and everything will continue working as normal. After the log header, there are all the owner blocks. Owner means connection. What can we see for every connection? Number. It's the identifier of the connection in the log table. It's, as I said before, it's the offset in the log table. Process ID. You can easily detect the process which represents this connection and this owner, and decide whether you need, for example, to kill it and so on. Well, I'm running Super Classic now, so all the owners have the same process ID. For regular Classic, there will be a different process ID, of course. But at the same time, there is a thread ID reported. In Super Classic, different connections are handled by different threads, so this information could also be useful if you would like to debug the engine or something like that. How many requests has this connection? So how many logs does it need in different kinds? Here you see the numbers. And the flags I was talking about, they are reported as a numeric value and with some abbreviations. The signaled, the owner has been signaled, the owner has been waked up, and so on. The owner is currently waiting for the log. The owner has been signaled by another owner, and so on. This is just the basic information about your log table. What can be obtained from this simple call? For example, if you have your application, your database, maybe some connections, maybe the entire connection set get frozen, locked up for whatever reason. You don't know what's happening, the CPU is not utilized, but new connections could not be established, or perhaps some error is reported, or perhaps they are also freezing, and you want to know what is happening. The first thing you should think about is whether it's related to the log manager. And the first thing you do, you run the log print utility with and without the C switch. If the C switch freezes as well, it means that the mutex cannot be granted. It means that some process has not released the log table mutex and thus is blocking everyone. In this case, the field active owner shows actually you the offset, the ID of the connection that is currently having this log. So you just scroll down, find the owner block. Of course, if your call with the C switch freezes, you just press Ctrl+C and then runs again this utility without the C switch in the data read mode. You just find the owner block with the number corresponding to the active owner. You detect what is the process ID. Just go to the task manager and use the kill utility and kill that process and see whether it improves the situation. At least it would be much better than killing everyone or killing them in the random order in order to see whether it helps or not. This is the simplest possible use of the log print utility. You don't have to analyze the output much. The default output is okay. But if you still have the connection frozen, but the log print call with the consistency switch works and reports that everything seems more or less okay, then it's not the mutex that is causing the problem. Something else is wrong inside the log manager, inside the log table. Perhaps some owners, some connections do not release the logs they have to. So in this case, you will be trying to analyze what's going on. Let's see how it could look like with a real test case. Here are the log tables generated with log print utility with the M switch in the HTML mode. This one has been generated using the W switch. It reports the waiters. What can we see here? Log header. Again, the default size, not much used, still there's some free space. Mutex weight is big enough, but hash lengths are still small. So the hash slot value should not be increased. But the mutex weight ratio, not maybe really a problem, but something to analyze why is it so. The W switch prints the queues of waiting. Here we can see the owner, this one doesn't wait on anything. The next one doesn't wait on anything, and so on. Here we see that this connection, process ID, this, waits on another process, which in turn waits on the third one. And the last one doesn't seem to wait on anything. But it's blocking this connection, and this connection is blocking this connection. So we have not a deadlock because this list is not recursive. The log manager detects the real deadlocks and will report here. For example, if this connection would in turn be waiting on that one or that one, the log print utility will not enter into the infinite loop, but it will report that the deadlock has been detected, and these are two guilty connections. But here, it's not the case. Okay, we remember, here we have a connection that's possibly problematic. Go further, nothing interesting. Again, the same connection. Another is blocked, but the same connection is guilty. Okay. The same situation. This, well, the more loaded connection, but actually, finally, in the final step, the same connection ID can be seen. We need to check what is wrong with that connection. Okay, click. Here we have If you didn't generate the output with AMP switch, you just have to find the string with any text editor. So if you don't have hyperlinks, you just remember this value, and you just have to find the string, start with the owner block, this number. So we have the connection ID of the connection that is causing us problems. Usually, you will see here the block list. So the requests that are blocked by this connection. So it could be time to analyze these requests, why they are blocking and so on. Here it's a more problematic case. There doesn't seem any blockage, but it would be interesting to see what connections, what locks are currently blocking others. So here another log table output is generated with the A switch. Everything has been reported. It's big enough. It's 2 megabytes. And what we need to check. Just wait. Slowed it. We are looking for. Okay, let's first don't scroll down a bit. Here we have owner block, the first owner block, the first connection, and all the requests are done on behalf of that connection, and so on. It's repeated for every owner, and at the end you see log block. It means the resource. For example, series number 3, it's a page log. Page space number 1, log, page number is 56. And the requests currently accessing this log, referring to this log. You can see that its state is 3. It's a protected read state. So it's locked in the protected read mode. Who is locking then this page in this log? A number of requests. Currently only one request. You can go to that request and see. So yes, it's holding the log in the protected read mode. There can be many requests. You can see that what particular connection has this log right now, and go to its block and see its process ID and so on. You just need to understand that every number here is the offset, and you can navigate to them using this number prefixed with owner block, request block, or log block. You just need to find this piece of information inside the log table and see what is actually interesting here. I see my time is already over, but just one more example. What blocks are currently blocking anyone? For example, you haven't run the log print utility with the W switch, or perhaps you did, but you want to find some other information and so on. Let's see who is blocking anyone. Commonly, this problem is related to page locks. For example, let's see. Page locks can be acquired in the shared mode or exclusive mode. Of course, shared mode doesn't block anyone of the same level, but shared blocks can block exclusive blocks or exclusive locks. So, search for state 0. Here is the magic string to find, and we see block number, this one, it's page 1129. It has 2 requests. It's granted the shared lock, and here are the 2 requests. State has 2 numbers. The first one, it's the current state of the lock. And in the parentheses, you can see the requested kind of the lock. Here we see that the lock is granted in the shared mode. This is the request that is holding this lock in the shared mode. You can see the owner, process ID, and so on. But you can see in the queue another request. It doesn't have this lock granted at the moment, 0, but it's requesting the state 6, exclusive mode. And the first one is preventing it to be granted. So the first request is blocking, and the second one is pending. Look at the flags. 2, it's pending. Okay, correct. Here we have, it's not blocking, but it's blocking seen. So we know that this owner, this process has been signaled that the blocking notification has been seen inside the log table. The AST routing has been called. The log has been attempted to be released. So we replace the blocking flag with the blocking seen flag, but the log is still granted. So it couldn't be released immediately, and it has been delayed until this process ends to read this page. This situation is perfectly okay. There are no any blockage. It's just a temporary situation waiting for the log to be granted. The same situation, but with more requests in the queue. Again, we have some process blocking the page in the shared mode. Another one is requesting the exclusive access, but it's not has been granted yet. It's in the waiting mode. There are other connections requesting the shared log, but because the ordering is honest in Firebird, so the log order is provided and guaranteed, these requests are waiting because of the exclusive request having in the queue before them. So even if they are compatible with the current log type, they can be granted because the exclusive request has been granted before them, because it has appeared clearly. So this is also, the situation is okay. What if you could see here not the value of 100 in hexadecimal form? Then it would mean that the AST has not been called, so the blocking process still has no idea if it's blocking anyone. And here you should analyze what was wrong. You check the owner of the owner that currently holds the log. It has been waked up, okay, but for example, it hasn't been signaled. Then something is wrong with the IPC communication in your setup. Some event or semaphore could not be delivered. If the owner block has been signaled, okay, it's good, but as the AST has not been called, the blocking notification could not be delivered on that process, then something is wrong with the log manager itself. I know such situations happens, for example, if some cross-process event has been missed, and the log manager starts to wait indefinitely and in the endless loop until the next event that could not be sent. So the final point is that, of course, the log table is a complex thing and the output is quite cryptic, but it's not really that cryptic. It can be analyzed, maybe even the half of the information available there, maybe even a little bit less, but anyway, it still allows you to first easily see the current load on your database in whatever Firebird version, even without the monitoring tables. Not only the load that's represented by the number of connections, but also the load represented by the high mutex weight ratio, so the connections are highly contending for the log table, perhaps very long collision chains and so on. And even if the performance is okay, you still could use the logprint utility to analyze what is currently blocked, what is currently waiting for, and what are the guilty processes. And even if you don't have an intention to start the debugger and try to understand the source code and why it's blocking and so on, you could still find the guilty process and decide maybe to kill it and see whether it improves the situation. This is quite easy to do for everyone here, with understanding of these thorough ideas, these simple ideas presented in this session. So I'm very much late, I see. So my apologies to the organizers, but really it was hard to shrink anything and remove anything from this presentation. So I believe it's not time to ask questions, so please get to me after the break or on the lunch and so on if you have any questions. Thank you for your attention.